This is a recording for section 14.2, Euler paths and Euler circuits. So we defined paths and circuits in 14.1. Remember, a path was started at one vertex and ended at another. A circuit starts and ends at the same vertex. But if we want to talk about an Euler path, it's a path that travels through every edge of a graph once and only once. So before, if we had four vertices and this was A, and this was C, and we wanted to write down a path, we could write down a path A, B, C. But if it's an Euler path, it has to hit all edges. So for this particular graph, we'd have to go A, B, C, D. All right? An Euler path has to touch every edge once and only once. So again, and it says no edge can be retraced. An Euler path must start and end at odd vertices. So if we look at this one, the labels on the sides indicate the order in which they're traversed. So here we go, A to B, that's for 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice that we've traversed every edge exactly once and started and ended at different vertices. And this vertex A was an odd vertex. It has degree 1, and vertex, I guess that's a G. Vertex G also has degree 1 because there's one edge out of it. So that is going to be a requirement for an Euler path, is that there's exactly 2 odd vertices. An Euler circuit, so just like the Euler path, it's going to have to travel through each edge of a graph once and only once. That is Euler, has to do with edges. All right, you can kind of remember the E with the E. Has to travel through each edge once and only once, but this one's going to, since it's a circuit, it's going to have to start and end at the same vertex. All right, so here is one that starts at A, and they're labeled again 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we've traced every edge exactly once, and it started and ended at A. But not all graphs are going to have an Euler path or an Euler circuit. So we're going to decide which ones do and don't. But it looks like we have one more example. Label the edges starting and ending at P to create an Euler circuit. So we're going to start at P. So there's many different possibilities, right? It tells you that here. So I'm going to label this 1, and then we're down here. And then maybe label this one 2. So we're going to go 1, 2, and then you put the little directed arrows on there to indicate the direction. So we're back here. So maybe we'll go 3, 4, 5, 6. Right, that's a separate vertex or separate edge because there is a vertex there. 7 and 8. So notice we started at P, we ended at P, and we traced each edge exactly once. So that is an Euler circuit. But yours might look different than mine depending on which direction you started. The following statements are true for connected graphs. Again, that would not have a circuit if it was not connected, right? So this is called Euler's theorem. If a graph has exactly 2 odd vertices, then it has at least one Euler path, but no Euler circuit. So we talked about that with 2 odd vertices of the path. You start at one of the odd ones and end at the other. Each Euler path must start at one of the odd vertices and end at the other, which is what I just said. If a graph has no odd vertices, it has all even vertices, then it has at least one Euler circuit, which by definition is actually also an Euler path. An Euler circuit can start and end at any vertex, right? Only we have to worry about if it has exactly 2 with the Euler path, that we start and end at the odd. If a graph has more than 2 odd vertices, then it has no Euler path and no Euler circuit. So they either have to all be even or exactly 2 have to be odd. Does the following have an Euler path, Euler circuit, or neither? Explain. If it has an Euler path or circuit, give one. So let's go around and list the degree. We have to decide if the vertices are even or odd. So let's go ahead and list the degree. This has degree 2, so that's even. 1, 2, 3, 4. That has degree 4, so that's even. 1, 2, 3. That's odd. 1, 2, 3. That's odd. 1, 2, 3, 4. That's even. And remember that even though these cross right here, there's not a point there, so a labeled vertice there, so there's not a vertex there. So if you notice here, this one has exactly 2 odd vertices. All right, E was odd, it had degree 3. D was odd, it also had degree 3. So it has exactly 2 odd vertices. And if you look at the last slide, if it has exactly 2 odd vertices, then there's an Euler path. And so remember, for an Euler path, you're going to start at one of the odd vertices. So let's go ahead and start it at D and end at E. You could do it the other way too, start at E and end at D, but here are your 2 odd vertices down here. So you're going to have to start and end at one of them. So again, let's go ahead. When we it says if it has an Euler path or circuit, give one. So we're going to start at D. All right, and it doesn't matter where you go next. You can go to E next. You're just going to have to end up there. In the end, it doesn't matter. E, let's go to B, A, C, to E, B, C, D, and E. All right. So we started at D and ended at E, and we've traced every edge exactly once. If you don't already have one, I would highly recommend getting a highlighter for this graph theory section. It's going to be very helpful when we start doing some algorithms, so with tracing graphs. Again, there are many possibilities in terms of answers. I just happened to find one. Do the following have an Euler circuit? Why or why not? And if you look at the first graph, you don't even have to look at the degree, right? Remember, Euler circuit means all even vertices. But if it's not even connected, you can't even make a circuit. So this one, part A, I'm not even going to figure out the degree of the vertices because this is not even connected. Right, it has to have all even vertices and connected. So part B, it is connected, so I'll go ahead and find the degree. But if you find one odd one, you can stop. So 1, 2, 3, 4 for that one. 1, 2, 3. And we can already go ahead and say no. C is odd. All right, they must all be even, so you find one that's odd and you're done. Now let's look down here. Again, it's connected, so we'll go ahead and find the degrees. This has 2 edges coming out of it. 1, 2, 3, 4 again. 4, 4, 2, 4, 6. So this one does have all even vertices, right? All the degrees were even, 2, 4, and 6. All even vertices. So that one will have an Euler circuit. We don't have to list one in this question. It doesn't ask you to list one. All right, now we're going to revisit our graph of Königsberg. Again, let's go ahead and draw our graph version of this. We had the right bank, the island 1, or now it's actually labeled island A, island B, and our left bank. And there was 2, those land masses, remember, are the vertices. And from here to here, there are 2 bridges. So we put 2 edges. All right, and from island A to the left bank, there's also 2. And there's a bridge here, a bridge here, and a bridge here. So this was the graph that we drew in section 14.1. And again, if you ever need to pause this to catch up on the writing, right, I'm kind of going fast because I expect you to pause it as you need to keep up. So is there a way anyone can walk across all of the bridges beginning and ending at the same point without having to recross any of them? So, right, we're not going to want to try to do this. You know, I mean, if you do, oh, you're stuck there, then you have to go back on one that you already went, right? So we don't need to sit and try all these possible combinations because we know if we want to go across all the bridges, which are the edges, without recrossing any of them, we want to know, is there an Euler circuit? That's what we want to know. You could sit and try it, all right? Start at one vertex. And then you'd be stuck, all right? You can sit and try it, but we have a way to answer it. Is there an Euler circuit? So we want to know, i.e., all even vertices. Again, to have an Euler circuit, we have to have all even vertices. So let's go ahead and count them. 1, 2, 3, we're done. Nope. Has at least one odd vertex. But if you look at this, so this has degree 3. This has degree 3. 1, 2, 3, 4, 5. So there's this one, actually, there's no even Euler path because there's not exactly 2 odd vertices. So there's no way to even start at one landmass and end at another and go over all the bridges. So there's no Euler path or Euler circuit. Oh, that's exactly the next question now I see, which I answered already. Is there a way anyone can walk across all of the bridges beginning and ending at different points without having to recross any of them? So I just answered that, but we'll just draw it out real quick. All right, this had degree 3, this has degree 5, this has degree 3, and this has degree 3. And the answers, again, if we want ending at different points, that means Euler path. And to have an Euler path, there has to be exactly 2 odd vertices. So no not exactly two odd vertices. So Fleury's algorithm, finding possible Euler circuits and Euler paths. If Euler's theorem indicates the existence of an Euler path or Euler circuit, one can be found using this procedure. If the graph has exactly two odd vertices, choose one of the two odd vertices as the starting point. If the graph has no odd vertices, choose any vertex as a starting point. And then number the edges as you trace through the graph according to the following rules. After you have traveled over an edge, highlight it or erase it. Show the highlighted or erased edge as a dashed line if you want to. When faced with the choice of edges to trace, first choose any edge that's not a bridge. A bridge is an edge whose removal would make the graph disconnected. Travel over a bridge only if there's no alternative. But I think you can kind of look at it. You don't really need to follow that algorithm. We just came up with the Euler path on the last graph without following any algorithm. Let's find an Euler circuit. We first need to check that they're all even. And this has degree 2. This has degree 4. This has degree 4. This has degree 2, and degree 4. So it does have an Euler circuit because they are all even. Sort of what I do when I kind of start at a vertex that has a higher degree. So I'm going to start with F maybe instead of E. I'm actually going to use a different color because that blue kind of looks like the blue that's already there. So I'm going to start with F. And I don't even think you need an algorithm. You can just kind of go around, right? F, B, D. If you want to label them, you can. 1, 2. Doesn't matter. You can go to anything now. Let's go to A, C, D, F. Again, we're ending at F, C, E, and back to F. See, we don't even need an algorithm. 1, 2, 3, 4, 5, 6, 7, 8, 9. So again, maybe just start at a vertex that has a higher degree. Sort of that's kind of what I do. So when we are asked to Eulerize a graph, we want to add edges to make a graph to make all edges, all degrees even. That's called Eulerizing. In this course, Eulerizing a graph is limited to duplicating of existing edges. So in real life, duplicating of existed edges means you reuse some of the edges. And so, even though there may not be an Euler circuit for, say, a garbage truck to go pick up garbage all over the city and only go down a road, each road exactly one time and start and end up at the same place. It may not be a possibility, but we can look at Eulerizing a graph and just duplicating existing edges, i.e. going down the same road more than one time, just twice. We wanted to go down those roads the least number of times that we have to. Right, to save money and time. So, do the following have Euler circuits? If not, what is the minimum number of edges that can be added to create an Euler circuit? Again, adding an edge means going down a road that exists. So you can only duplicate an edge that's already there. So here's sort of the process I use. Circle the odd vertices, then join the groups of odd vertices using the least number of edges. where there is an edge already, right? So let's first look and see if these have Euler circuits. This has degree 2, degree 2, degree 4, all right? 1, 2, 3, 4, degree 4. This has degree 3, 2, 2, and 3. So this would have an Euler circuit except for the two odd vertices. So we circle those odd vertices, and then we join them. If there is an edge there already here, this one's a piece of cake because there's an edge there. So this just means if the garbage truck will have to go up and down this road twice. All right, so we would add one edge. All right, and then then if you count now, 1, 2, 3, 4, 1, 2, 3, 4, then now we have made these even. So all the vertices are now even. Let's look at part B. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. That one does have a vertex there in the middle. 1, 2, 3, 1, 2, 3. So this time we have 4 odd vertices. 1, 2, 3, 4. And we want to add edges, again, where edges already exist. And any time, right, we add an edge to an odd vertex, it makes it even. So we want to connect these, and there's several ways to do that, but you're going to have to connect the pairs, so you can add an edge there and an edge there because their edge already exists. Then that will make these all have degree 4. Okay. You could have, so you want to add the least number of edges. Here we had to add 2 edges. Okay. You could have also connected it. You know, there's several ways you could have done this one. All right. You could have, if you circle these odd edges, you could have done something, these 2 and these 2 as well. Right? It didn't have to be that exact scenario. So we have one more example here. This one's a little more difficult. How many edges should be added to find the best Eulerization? So again, what we're going to have to do is circle all the odd vertices. All right, so this one has 2, so that's okay. I'll use a different color. This one has 3. This one has 3 edges coming out of it, 3. So again, we circle the odd vertices. This is odd. This one has degree 2, so that's okay. Odd, odd, 3, 3. That one's 2. Odd, 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 even, odd, 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 odd. So that's what the outside looks like. This one's 4 edges, 4 edges, 4 edges. So those are okay. 4, 4. This one has 3, so I'm going to circle it. 4, 4, 2, 4, 4, 4, 4, 3 again, 4. So we want to do the best Eulerization, which again means the least number of edges that we're going to add that already exist. So you can kind of see with the ones that we've circled, again, you connect 2 odds to make them both evens because you're creating an edge out of each one. So you can see these ones on the outside, it's sort of begging you to do this. All right, those will now all be even. So I've added 2 edges down there. Those, and I'm adding the edge there because there's an edge that already exists. Again, this edge and this edge. Now that Those will then have degree 4. Now I have the two guys in the middle. You can't put an edge like across here because those vertices, there isn't an edge that exists there. You're going to have to go around where edges already exist. So I'm going to have to add 1, 2, 3, 4 edges to connect those two. And it doesn't matter which direction you go, it's 4 both times. I can tell based on this graph that that is the best I can do, right? So we've added 1 edge, 2 edge, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've added, how many edges should be added? And the answer is 12 for the best Eulerization. There's other possibilities, but that's the best that we can do, the least number of roads that we would have to retrace. Again, that for Eulerization, circle the odd vertices, connect the odd vertices with each other using the least number of edges, but that the edges already exist.